Hi, everyone. Today we have the pleasure to host Peter Boswijk from University of Amsterdam as a guest speaker for our time series seminar, and Marine Carrasco from University of Montreal as guest panelist. If you have any questions during the talk, please feel free to unmute and ask your question. Thank you. And Peter, the floor is yours.
Thank you, Adriana. The pleasure is mine. We are a bit late because of technical issues that I just had, and I hope that they will be resolved now. This is joint work with Roger Laven and Yevgeny Vladimirov. The latter is our joint PhD student who has been working on trying to extract information from options. If you can go to the next slide, please. So indeed, the idea is that if you have a set of options for each day, option prices for different strikes and different maturities, then that will have important information basically on the risk-neutral distribution of the underlying asset and perhaps the stochastic process that drives that underlying asset. Now, there is a long literature on the econometrics of such models. Typically, it started with the idea that you can perhaps back out implied volatilities or parameters from comparing model-based option prices with empirical option prices. And you could do this in a nonlinearly squares type framework or something a little bit more elaborate, a bit more advanced, where you look at moments and try to fit those moments, like in the efficient method of moments, or you use GMM, as we have been doing in another paper, using a continuum of moments, actually making use of the work of Marine in this area. And then there are other approaches.
Peter, we cannot hear you. Maybe we can leave the recording.
You are on mute.
Sorry. Can you just continue? Can we continue? Sorry again. Let's hope that this is the final one.
Yes.
And if not, then I can keep on apologizing. I'm supposed to be head of the Amsterdam School.
Peter, I think your audio dropped off again. We can't hear you.
Yes, we can interrupt the recording. Maybe that's the problem. And we just don't record, or I don't know. Shall I stop the recording then?
I would stop the recording, actually. Yeah. What do you think, the others?
It could be that his problem. It's too much.
Let's maybe we wait, Peter.
Yeah.
Okay, let's wait a second.
I feel a bit bad, sort of testing your patience like this.
So let's try one more time, and then we can stop the recording and then try again.
Yeah. It's. I was actually thinking of doing this from home, where my Wi-Fi is better, but I should have done that, I guess.
No worries. I mean,
I have been Zooming a lot with people, but okay. Okay, back to my talk for the time being, at least. I mentioned that there is a relationship to some recent work. What we do actually, before I get kicked out again, let me mention that at least, is that we have what we think is a new approach. What we do is we look at not so much the option prices themselves, but a transformation, which is an estimate of the characteristic function of the underlying. So we transform option prices into characteristic functions, or let's say log characteristic function observations. And then we have a model-based version of that same log characteristic function. And the coupling of these two is what can be done in a linear state space model, right? So the basic idea is rather than trying to use these methods to evaluate option prices, we kind of transform them back, the empirical option prices, into characteristic functions. And then if you take the log characteristic function on the left-hand side of your equation, then on the right-hand side, you can have your latent states, or you can have your model-based parametric form. And those two together basically then will be coupled together in a state space representation. So at least I've given you the bottom line. Let us go to the next slide, please. Okay, so the way I'd like to do this, speeding things up a little bit, is to give you a little bit more of an extensive motivation, giving you the basics of option pricing, although I guess many of you have been working with this, but perhaps some of you haven't. And then it helps to actually visualize some of these things. Then I will show you how we can indeed transform a panel data of options, of option prices, to an empirical counterpart of the characteristic function. And I should say it's a conditional characteristic function. So it's going to be time varying because of this conditioning. That will be our left-hand side variables. Then we couple that with the right-hand side, which is a theoretical model from the class of affine jump diffusions. And because of that affine assumption, essentially, we end up with a linear measurement equation. And in fact, from the same class of processes, we also get a linear transition equation. So that means that we have two sets of equations, measurement equation, transition equation, which together is a state space formulation. In doing that, we use a particular kind of asymptotics, namely we assume that the number of strike prices for which we observe option prices tends to infinity. That is to say, we fill in the entire real line of strike prices basically as n, the number of options that we consider, tend to infinity, right? So the main result is actually one in which we see to what extent this state space formulation is valid. That is to say, we have some approximation errors and how quickly those approximation errors basically tend to zero as we take this infill asymptotics. I should again mention that this type of asymptotics is not new. There have been many others who have worked with the idea of having a continuum of strike prices. So that has been used a lot, and we use it here to actually demonstrate the properties of the state space formulation. Once we're there, estimation of the model is just by the Kalman filter, or perhaps a modified version of the Kalman filter. That is not where we have many new results. It is more in the representation and on the properties of this representation, the validity basically of this representation. So then if I have time, I will show you some simulations and of course an empirical application. Let's move to the next slide. Great, thank you. This really, excuse me, starts from the basis. What you should see in front of you is a time series of an asset price. We call it FT, where F is really for a forward price, but the distinction between spot and forward is not very important for most of my talk. We are now at time small t, and of course we want to see what happens with the stock price perhaps at time capital T, because this is where options have their payoff, right? So cap T minus small t will be the time to maturity of our option, and we will use the letter Greek tau for that. If you do another click, Majid, then we should see some further. Wonderful drawings, aren't they? These are done by Evgeny, of course. So these are not just one path, but many potential paths that the stock price or the forward price could take from time small t. And if we plot all those, then of course you get an impression of a distribution, a conditional distribution, that is, of the future stock price or forward price given the current one. Yes, and that's this density that I hope you see right there. We use the letter Q there. Q stands for a risk-neutral density. And if you're familiar a little bit with option pricing and no arbitrage pricing, you know that the no arbitrage value of a derivative is basically the discounted expected payoff, but then under a risk-neutral distribution. So that's why we use this Q right there. One more click. Leads us to the value of the option. What is an option? Well, for example, here we see a put option with a strike price K, and that gives a payoff of K minus F. If FT, the final value of the stock price or the forward price, is actually below the K, and if it is above it, then it will have a zero payoff. So that is this, I guess, purple part of the density that I hope you see there. At least my interpretation of it is purple. So essentially the price then at time small t of this option will be the expected value of that payoff using that risk neutral distribution. And then one more click. That of course is a function of this risk neutral density. And of course, this risk neutral density in turn is probably derived from a dynamic process for FT, right? We have a model for FT, how it evolves from time small t to later. That gives us a density for a particular maturity tau, tau being the difference between capital T and small t. I hope you also see that if we have more than one strike prices, then we get many, many options. And with the prices of all the options, I hope you agree that we basically map out this risk neutral density, right? It's like we get from the density to all these prices or back, basically. That is the basic idea of what we're working with. And if you would like to click once more or one, we see indeed that we can go in two directions. The natural thing would be to start with F, with the stock price or the forward price, a model for the evolution of that price, and then derive from that what the value of the option would be. Black and Scholes did this, of course, way back then. They assumed the log normal density, and that gave you a closed form solution for the Black and Scholes price. So that's nice. It's a closed form expression. If you go back basically from that and you say, well, let's plug in an empirical option price and let's back out which value of the standard deviation would actually match the theoretical Black-Scholes value to the option price, then you get the implied volatility. That's in the third bullet point you see right there. And this implied volatility, if the Black and Scholes model would be correct, would be a single parameter sigma. So if you plot that for different strike prices and different maturity, that would have to be a horizontal surface or a plane rather. Because that does not vary with K or tau, the time to maturity. Of course, you can reverse direction, excuse me, and go from O, the price of the option, back to learning about the dynamics of FT. For example, if you calculate all these implied volatilities for different strike prices and Ks and plot those implied volatility surfaces, then you can check whether this Black and Scholes model will be sufficient or whether you need something more elaborate. And the typical thing that we see is that actually these surfaces are not planes constant over time, but they vary over time in height, but also in terms of curvature and slope. And therefore, we need something more to actually drive the evolution of the underlying to get better fitting option prices. And one obvious example would be the Hester model, which allows for stochastic volatility. So then we have one stochastic process that drives basically this surface. If you can go to the next slide. Then what you see here is an example on the right-hand side of such an implied volatility surface. with two axes, tau, the time to maturity, and k over f, which is the strike prices. And indeed, you see it's not a horizontal plane, but rather it has curvature. If Majid can actually click on the play button, if you see that, let's see if this works. Would be fun, right? Yeah. Then you see that over time, this surface actually moves. It goes up and down a little bit. Its steepness and its curvature might change over time. In particular, when we reach a crisis like the COVID outbreak, basically in early 2020, then you see a big change in this volatility surface. Right, so the right-hand side are essentially the data that we have to work with. These are these option prices for different strikes and maturities over time. So you can think of this as a functional time series. But of course, if we evaluate it at discrete point, you can also think of it as a matrix valued time series. But in any case, I hope you agree, it is a high dimensional time series, right? I mean, it has many points basically over time that we want to model, that we want to say something about. We're not going to use necessarily very high dimensional techniques because we would like to have the evolution of this entire volatility surface being described by a few stochastic processes, latent stochastic processes. Like you could call them factors, you could call them state variables, but essentially what we're looking for is that the evolution, the height, but also the changes in curvature and slope, etc., can be described by a finite and perhaps a small number of stochastic processes that explain this part, and that's what we're after. Now, of course, having this matrix valued observations or a large dimensional observation vector being linked to a few underlying hidden latent state variables, that is already a state space model, but right now it would be a very nonlinear state space model, or at least the measurement equations would be very nonlinear, because these option prices and also these implied volatilities are not necessarily linear in these state variables. So that's why we're going to use another transformation shortly. If you can go to the next slide, Brigitte. Thank you. This is indeed an example or a leading example of a stochastic volatility model proposed by Heston, where the forward rate F still is like a geometric Brownian motion, but now with the time varying volatility. That volatility process VT, it has mean reversion and it is driven by its own Brownian motion, which might be correlated with the stock price Brownian motion. Now, how do we do inference on the parameters of such a process based on option price data? Well, the simplest example, the nonlinear least squares type approach that I mentioned in my introduction, would be to say, well, confront the market prices with model-based prices and then calibrate or back out basically parameter values theta. Theta would be all the unknown Greek letters basically in the slide in the equation on the top of the slide, but also to back out VT, the spot, the current volatility basically, right? So that means that if you do that, you get a nonlinear least squares type problem where you want to solve out N, okay, sorry, N is actually capital T there. So the number, the time series number basically of observations plus 4, because there are 4 parameters here to calibrate. That can be done. It will be somewhat computationally intensive because the model evaluation, the model price evaluation involves sort of computationally demanding techniques. But perhaps what is more interesting is that in this way, you just use the cross-sectional information at each time point to back out the VT. Whereas it might make sense to also use the dynamics of the underlying process, at least if this is a somewhat persistent stochastic process, right? You would like to pull over time also information, and that is not really exploited in an approach like this. And in more elaborate GMM, EMM type processes, that might be a little bit more, but still there you would typically use the cross-sectional information at any point in time only to back this out. And this is what we try to avoid in our approach. Next slide, please. What then is our approach? We transform options to this an empirical counterpart of a conditional characteristic function. that is based on an important result by Ramadan, but actually it was also applied already by Viktor Todorov in a number of recent papers, in particular the one mentioned at 2019 here. So that is our left-hand side variable. Then the right-hand side will come from a class of theoretical models, the affine jump diffusions. And then if we marry those, if we couple those two together, then we get an observation equation part of our state space model. After that, step 4 will be to estimate such a model based on the Kalman filter and then plugging that in a Gaussian quasi-likelihood. So then you get Gaussian Kuhlmann estimation based on the Kalman filter. That is in a nutshell what we propose to do and what we also apply in simulations and empirical applications. The advantage of that is that you don't have this computationally demanding Fourier inversion, basically, that would require evaluating these option prices for different parameter values and for different time periods, etc. Right? So that can be time consuming. That we, at the same time, not only exploit cross-sectional information, but also the dynamic information, the time series information, that it is relatively simple once we have transformed the data to the characteristic equation. Yes, Maureen.
I have a question. Yes, you could also just evaluate the empirical characteristic function from the asset prices instead of using option prices. Would it work?
I would have to think about, if you look at the method that we use basically to get the empirical characteristic function from the option prices, then I think that would not necessarily generalize to just having a single underlying asset price. So at least our method would not be directly implementable, but I may oversee other methods that would also give you this. But right, so there is this cross-sectional aspect that will help us to actually back out the conditional characteristic function. Okay, so relatively simple to implement once this transformation is done, and because we're looking at characteristic function, we have the freedom to exploit basically all distributional information, probabilistic information. So in that sense, we don't have to confine ourselves to a couple of moments, for example, right? So that's basically the advantage of that. Okay, next slide, please. Thank you. So the way in which we get these observations, this transformation, in a few steps, we start from an old result by Breenan and Litzenberger, who show that when you have a continuum of strike prices and options associated with that, then actually you can back out the risk neutral density that I showed you earlier from the second derivative of the price of a put option. P here stands for put option, second derivative with respect to the strike price. And if you're curious about how that property comes about, it is actually just writing down the risk neutral valuation. That's the first display equation that you see, and taking second derivatives and using Leibniz rule basically, and you will see that result. Right, so that means, as I already hinted at, that if you have a continuum of options for a particular maturity tau, but with very many different strike prices, then basically if that is smooth enough that you can take second derivatives, then you could in principle get the risk neutral density for that. Now that has led to further ideas of the benefits of having continuums, a continuum of strike prices. There is a nice result by Kammer and Madan, which tells us that if you want to price not a put or a call option, but a general derivative with a payoff function g of ft, ft being again the forward price at maturity at time capital T, then you can actually express that risk neutral value in terms of call and put options at all the strike prices at the continuum of strike prices, because you see an integral here again, right? So you need a continuum of these strike prices. You see that we switch from put options to call options at the point ft. That means that we are always looking at out of the money options. And in fact, therefore, the letter OT you could interpret as standing for the price of out of the money options. Out of the money meaning that at the current price, the option would not pay off anything, basically. So that's what that means. The advantage of doing it like this is that actually these options, when you these out of the money options, when you plot them as function of k, basically start at 0, then go up and then go down again. So that has nice integrability properties, basically, that you would not have when you would focus only on call or put options. So this result, on the next slide, you will see we apply to a particular payoff, namely the payoff that gives us the conditional characteristic function. Of course, this payoff is complex valued. I is the imaginary unit. And it is functional because we now introduce a new argument u, the argument of the characteristic function. But if I take that for the function g, then I get the discounted, I should say, conditional characteristic function of, well, what you see here is not ft, but ft over f small t. So that's basically the log return. So this is the conditional characteristic function of the log return. So applying this function g basically to the general result of Karaman-Madan on the previous slide, you get an integral expression for the conditional characteristic function where we integrate over all the put and call options, out of the money put and call options, with a particular function that stems from this second derivative of the g function, basically, right? So now we have a way to recover the conditional characteristic function at time t from a continuum of option prices, all of them with maturity tau, because this also gives me the characteristic function of the return over the horizon tau. And of course, if I then vary tau, I get different results for each maturity. So this is nice, I think, but of course it is a little bit stylized and abstract in the sense that in practice we will not really have a continuum of option prices. So we need to transform or to replace this integral by a sum, I guess. And we will do this for a discrete set of strike prices k, hopefully observed at small intervals such that we get many of them and therefore can use this continuum as an asymptotic limit, so to speak, of the experiment that we consider for a finite number n of options. So the phi hat t that you see at the bottom of this slide is the estimated characteristic function. And it will not be the true characteristic function, but it will be the true one plus an error. And that error will reflect a number of different aspects, namely the fact that we have replaced our integral with the sum. So we have discretization errors. We will also have truncation errors because we can't really start the strike price at 0 and end at infinity. So we need to take an interval there, which truncates basically the whole real line. And then there will be measurement errors in practice between what might be a theoretical option price and the observed option price, for example, because of market microstructure noise or other kinds of deviations that we typically encounter. So that's why the zeta t that you see right at the bottom is an error, a composite error, if you will, caused by truncation, discretization, and measurement errors. Next slide, please. So this gives us now, once more, the left-hand side variables, the observations that we are going to work with, the empirical characteristic functions as I just described on the previous slide. What's on the right-hand side? Well, that's something that is determined by a model that we have, and the model will be part of this class here, where we have a vector, a state vector xt, which satisfies a jump diffusion with a drift, a diffusion parameter, and also a jump intensity function that are all affine in the state variable. This is what defines affine jump diffusions. And the Hessel model that I showed you earlier is, perhaps the simplest example that you can think of such an affine model. I didn't really draw the attention to that, but there the volatility was proportional to the square root of Vt. So if you take the squared diffusion, as you see at the bottom of the first bullet point right here, basically the outer product, then that will be indeed affine in the state variable in the Hessel model. But we allow for more stochastic volatility processes and multi-components, perhaps with a slowly varying short run, long run and a fast varying short run components. We also allow for the intensity of the jumps that might occur there to be stochastic and to be a stochastic process in itself. So that these are typically the examples that we think of. 1 or 2 volatility factors, perhaps an intensity, and if there's not enough, then you need more elaborate models, but basically they should all fit into this class. I should mention that capital X here contains both latent variables and possibly also observed variables. For example, in the Hefton model, you would have log FT, the log stock price, being basically an observed state variable and VT being a latent one. The nice thing about these affine models is that also the conditional characteristic function of the entire state vector is exponentially affine. So that's what you see right there, e to the power, let's say a plus b times x, basically, where a and b, or alpha and beta more precisely, are functions of tau, the time to maturity, and the parameters, basically, right? So this is why we choose, or why we like, for this particular application, this class of models, not only because it is fairly rich, but also because when we then take the log characteristic function, we get a linear expression. So if we also do that on the left-hand side with the log empirical characteristic function, then we get close to a linear measurement equation. The boldface U here is a vector, so that's for an argument for each of the components of UT, but we're only interested in the first one, namely the log asset price, and that's why we use this U1 expression, which basically puts zeros everywhere else to get from this joint characteristic function only the one for the log asset price. Yes, please, to the next slide. So what that means is if we take log left and right, then we get in principle a log characteristic function that will be affine in X. And then if we replace the true basically population characteristic function by our empirical counterpart, then of course we introduce measurement errors again. That's these xi-t's, as we now call them. The xi-t's are not really the same as zeta-t's, but as we introduced earlier, but that has to do with the fact that we log linearize, so to speak. So in that sense, there's something a little bit more going on. I hope you're not too much distracted by the beta tilde. This is because we need to go from log prices to log returns, basically, and that's why you need a small modification, but it's not really important. Now, if the entire xt would be observable, of course, you could do nonlinear least squares in some way or another to estimate the parameters. But what we have here is typically that at least part of xt will be latent, and therefore we're going to use some kind of a way to filter that out, basically. There is a relationship of this to affine term structure modeling, yield curve modeling, as some of you might have been involved with. There you also have like a functional dependent variable, but they go in one direction, namely the maturity, right? The yields to maturity. And what makes that simpler is that typically the left-hand side variables are just yields. You don't have to transform them into something to just get directly a linear relationship between the y's and the right-hand side variables. So that in that sense, that is simpler. But other than that, in spirit, it is basically closely related to that. Next slide, please. So if we have a functional measurement equation, because that was basically on the previous slide, we want to couple that with a transition equation, a dynamic equation for the state that describes the evolution of the states. And here we really want to make the distinction between the observed states W and the unobserved latent states small x. And it's only for the small x that we really need to have this transition equation. And because, once more, this is in the affine class of models, this will have a conditional mean and a conditional variance, which are both linear or affine in xt itself. So that makes this a linear transition equation. So the display on the middle of the slide is essentially like a VAR model, a vector autoregression for x, xt plus 1 depending on xt, as you are familiar with when you've seen state space models, basically. With an error that has a conditional variance that itself is also affine in the state variable xt. So the q of x is going to be affine. all these components that I've now introduced, the intercepts, the VAR matrix T, the variance matrix, they will be functions of the states and of the parameters, basically. Well, not function of the state, but of the parameters in general, except the Q function. I should also mention that I've now suddenly introduced the letter P for the true dynamics, not the risk-neutral dynamics. In general, we would like to have a distinction between risk-neutral dynamics and true dynamics. In practice, we will not be able to identify very well the difference between them in the terms of risk premia, but I will come back to that later on. But in any case, the state transition equation is under P, under the true dynamics, basically. So indeed, if we want to couple these, then either we have to introduce risk premia, or we have to make an assumption about risk neutrality, basically. That's kind of the bottom line. Okay, next slide, please. So we already had a functional valued measurement equation, which we're now going to turn into a vector valued measurement equation. Of course, one could do perhaps functional Kalman filters or so, but we're going to keep it relatively simple by saying we're going to choose a grid of values for U, for the argument of the characteristic function. And we're going to choose, so there are K of those, no, Q of those, I should say. And then we have K different strike prices, no, back out. We have K different times to maturities, and Q different arguments of the characteristic function. And then, of course, these are complex valued, so we're actually stacking the real and imaginary part of those observations. So that gives us 2 times K times Q observations within the long vector YT, right? So now finally we end up in a linear state space model. On the left-hand side is Y, on the right-hand side is X, the latent states, basically. The epsilon is a transformation of the psi t in a similar spirit as this stacking that you see at the bottom of the slide. What is new perhaps now is that we have explicitly allowed for an approximation error or a remainder term, which involves basically this log linearization, but in this remainder term, we're also going to collect the errors due to basically discretization and truncation of the integral that I mentioned earlier, right? So we have a proper epsilon that would be there because of measurement errors, but in the absence of these complications. And we want to say now something about the behavior of this remainder term, because if that is small enough, then we may proceed with the state space model basically and apply the Kalman filter to that. That's basically the idea of our results. Let's see what's on the next slide. So in order to get to a result, namely that as we get to a continuum of strike prices, this remainder term, this approximation error, if you will vanish. We need, of course, to make assumptions, namely that X is indeed follows an affine jump diffusion. If you look at this literature, then you see that you need to be a bit careful about admissible parameter values, meaning parameter values such that volatilities are positive and things like that, basically. So that needs to be assumed. We need to say something about the structure of the observation errors in the option prices. And we're making a rather heroic assumption here that these are independent over time, but also over different strikes and different maturities. And of course, one could perhaps have something a little bit more realistic, but for now, this is the assumption that we are working on. There's a complicated expression for its conditional variance, but in words, what this assumption means, that we think of implied volatilities having errors that are a percentage of the level of the implied volatility. That's basically how you should interpret it. So the sigma var kappa squared or so that you see middle display at the beginning of the right-hand side, you can think of that as the variance or the standard deviation as a proportion of the implied volatility. And that's basically what this assumption boils down to, which we think is fairly realistic. We could have other assumptions. It doesn't hurt so much, but this helps us to basically get to some results. We need to assume the existence of at least some moments. And then, of course, the real assumption is that these strikes, there are n of them, n tends to infinity. And as n tends to infinity, we fill up the entire real line, which means that the smallest strike has to go to 0, the largest strike has to go to infinity at a certain rate, such that also the delta between the strikes, that is to say the grid, the mesh basically tends to 0 as well. So that is possible. Of course, it is an asymptotic assumption, so to speak. In practice, we will have to make do with the options that we have, but we believe that this is a realistic way of thinking about asymptotics in this framework. Under these assumptions, we get a result. That's on the next slide. And the result is, yes, we end up with a state space model as we have just derived, basically step by step, where the errors satisfies the usual orthogonalities, basically, over time and with respect to each other's, where there is an expression for the conditional variance matrix of the epsilons, the measurement errors, and that is actually a function of, well, the underlying state variables in a rather complicated way, and one single unknown parameter. So that basically makes the whole analysis feasible in terms of doing Kalman filtering with HT. We need an expression for HT there. The transition equation we already discussed, also that this Q will in general be affine. There are specific cases where Q will be constant, but if it is really varying with XT, then that is something that we will have to address, and we will come back to that if I have time, because I need to speed up a little bit. The first bullet point here is the real asymptotic result, namely that if we use this scheme and these assumptions that I just described, then the epsilons will actually, so the measurement errors, the errors in the observation equation, the measurement equation, will tend to 0 at a certain rate. That basically says that, yes, as we get more and more data, all these like noise errors are averaged out. But more importantly, that these remainder terms, log linearization, truncation errors, etc., that they tend to 0 faster than that. It's not very nice. It doesn't look like the type of orders that we are familiar with, perhaps, but they tend to 0 at a slightly faster rate, which would justify well, basically ignoring them in what follows. If you really want to make that stick, basically, to make that formal, you would have to look at asymptotics of the Kalman filter, basically, of the QML based on the Kalman filter, and see whether indeed this remainder term vanishes from those expressions. We haven't done that in this paper. We just basically give a result for the representation where we have an approximation error that tends to 0 at a certain suitably fast way, basically relative to the errors, the epsilons in the that are always there in the measurement errors, basically. I hope this gives you an idea of the theoretical results that we have obtained, because I think from here on, I'm going to make a few remarks about estimation, and then I'm going to show you some simulations with the time that I have left. So on the next slide, yes, that's the slide that we're going to. I'm going to say just a few words about. If we have many of these points U, few of them, and many different maturities, then we have a very long observation vector YT. So it's high dimensional. That means that you might have to take special care of how you do a Kalman filter. Fortunately, Simeon Koopman and his co-workers basically have devised a method which is called the collapsed Kalman filter, and that's the one that we apply here. We modify it a little bit to allow for an H, a variance covariance matrix that might be singular, that might have 0 eigenvalues, basically, and that's what makes it slightly non-standard. But other than that, we basically follow the literature in that respect. Next slide, please. A remark about QML estimation. If this Q is really a function of the state variable XT, remember Q is the variance covariance matrix of the errors in the transition equation. What you could do is well, first of all, if it doesn't vary with XT, then yes, we have this nice result that even if it's non-Gaussian, the Kalman filter delivers minimum mean squared error predictions. And that indeed is an ingredient in showing that, that Gaussian QML in these models is consistent. The unpleasant thing is that when Q does vary with XT, then there's a very natural thing you can do. Namely, you can take the most recently filtered state, plug it into Qt, and do the Kalman filter with that method. It's a very simple and perhaps obvious way of updating the Kalman filter. It is sometimes called the modified or a modified version of the Kalman filter. And people have done this before. Frank de Jong from Tilburg has done this in a paper about term structure in the past, and others have come to the same method. It seems to work very well, or reasonably well, let's say. Unfortunately, it's very hard to say something about the asymptotics of this. So there's no real formal theory for this, which we don't like, but we can't really solve either. So in that sense, we're just taking this method as given the linear state space representation that I've derived earlier, and hope that indeed in Monte Carlo simulations this works reasonably well. I suppose that I will try to stop at 6 for me or 5 for you, and then I will see how far I can come. Yeah. Okay. Let's move to the next slide then. We're going to look at a few simulation results where we have simulated a model with a stochastic volatility, where both the stock price and the volatility is driven by jumps. And these jumps have the same intensities, the same counter for the jumps, basically NT, but only the negative jumps in the stock price lead or are associated with positive jumps in the volatility. If there would be a positive jump in the stock price, that has no effect, basically. There's no contemporaneous jump in the volatility. That's basically what this specification implies. We assume that there's only a single latent state variable because the intensity is assumed to be proportional to the same stochastic volatility. So there's just one process. And there's a complicated looking double exponential distribution for the jumps in the stock price, which we have used in these simulations. So this is how we generate our data, first for the underlying, and then from that and from the model, the option prices, and then we add a little bit of noise to it and basically run our procedure. On the next slide. Thank you. Are some further parameters that we have set, 500 time series observations, daily data, 3 maturities, a finite number of strikes. I should look up the exact number, but basically we have the grid size in strikes as 1% of the current forward price. And then we add observation errors where basically the noise is about 2% of the level of the implied volatility. That's how you can think of this 0.02 squared that you see right there. There is something that I would rather avoid talking about too much. And of course, my co-author Yevgeny would be happy to talk about this later, but that we still need some kind of interpolation in these options. And that is not really reflected in the theory that we have, but in practice, that is what we need to do. Next slide. So these are some simple Monte Carlo results. There are some true values of the parameters, and in these only 300 replications, you could argue perhaps we could have done a bit more, given that the computational complexity is not so high, but okay. We end up with promising results for most parameters. The delta, which is the proportionality between the intensity and the volatility, is perhaps estimated the most imprecisely. I should mention here that we have not allowed for a risk premium in this model, right? So basically, we assume here that P is Q, and that helps things a little bit. Although when we do allow for a risk premium, then basically that risk premium is estimated very imprecisely, but the other parameters are estimated reasonably precisely. So in that sense, we could have allowed for it, and just acknowledge that basically this risk premium is harder to identify. We've tried 2 grids basically for the the arguments of the characteristic function. And in this case, it appears that I think in most cases, the standard deviation go a bit down. Although if you extend this further, then you will see that this gets worse again, basically. So this is a little bit something that is in the design. How many points do we take? What do we take in terms of an interval? And we try to think of ways to sort of calibrate it to a particular application where you can do, well, if not cross-validation, then something like that to choose these design or parameters. Good. Let's look at the next slide. Yeah, okay. This, I think we can. This looks perhaps too good to be true. Namely, that in this DGP that I've just shown you, this works quite well. Of course, the estimates were quite well. You should remember that this is where the noise, an example where the noise is relatively small. So in that sense, it's perhaps not so surprising. And of course, what you do see is that one time series follows the other, right? The estimates is lagging behind one period, as you would typically have in these types of models. So in that sense, it's not like you're spot on, even though it looks as if the filter of the volatility is quite close to the true stochastic volatility. Okay, perhaps the last couple of minutes, let's move to an empirical application. What we have is index options on the S&P 500. We take a period from 2017 to 2021, including therefore the COVID, the outbreak of the COVID crisis, as you know. We have a couple of different maturity tenors. And indeed, we have to filter out all the options that we have, which are many, filter out the ones that we really think are wrong, and also have some interpolation to let the noise be not too large, basically. So then bottom line is apply the methods, apply the same model that I just showed you in the Monte Carlo simulations, see what comes out. Well, the first 3 parameters are the estimates for the Heston type of specification. They are, I think, kind of in line with what you would typically see in this literature. You could say that these standard errors are a bit too small for comfort. That is to say, could we really trust those standard errors to be that small? This is something that we have to perhaps do some further work on, because I would say that that depends a little bit on sort of certain design parameters or tuning parameters that you have to set there, basically. So I'm not fully convinced, but in any case, we do get a nice set of estimates. One thing that I would really want to draw your attention to, not because it's beneficial for us, but because it's important, is the final estimate, that is sigma of kappa, that is now 0.25. So that's like 25%. So these are very, very big measurement errors, namely 25% of the implied volatility. So what that probably means is that this single factor, this single state variable model that we have right here is really insufficient, that there are more common factors in this set of options and therefore in the set of characteristic functions, and that one would need sort of more elaborate models, namely perhaps another independent jump intensity, or perhaps a more elaborate stochastic volatility to bring down these noise terms to something a little bit more manageable. So that is something that I would like to emphasize with this. I think we should probably move to the final slides then. What I skipped was an application.
If you want, you can take another 5 minutes.
Okay,
if
okay.
you want.
Thank you very much. I will just say it in words, basically. So I mean, we could go here. It is allowed that part of the state factor is actually observed. And we have some applications where we say, let's take an empirical time series, put that into the state factor together with the latent ones, basically. And because this was a little time episode where the crisis appeared to be dominated by the outbreak of COVID, we thought, well, let's take empirical data on COVID and see whether this works. So reproduction number there we plug into the model as an additional state variable. And the final bullet point here says that we don't really have a parametric model for this RT. But of course, you need it to price the options. So what we do in pricing these options is basically assume that the current level of that RT will continue to be the same basically over the lifetime of that option. One can debate whether that is realistic, but that is like a random walk type assumption basically that we plug in there. The price of not doing that would be that we have to have a well-fitting parametric model, which might not be so easy, basically. So that's why we opt for this approximation. So on the next slide, you see these reproduction numbers, two of them actually, but we use the red one. So that's the more non-unsmoothed version, which is basically a weekly change in the number of infections. And then on the next slide, you see the model that we are now fitting, where we have an additional Brownian motion in the stock price, which is scaled by these R's. That means that the total volatility, capital V, is now the original Heston-like stochastic volatility plus something that is related to these reproduction rates, basically. And similarly, the reproduction rate enters into the intensity, lambda, with a parameter gamma. And if you focus on those parameters, namely Q and gamma, you see that these are perhaps relatively not the biggest parameters. But if we trust these standard errors again, then we would say that these are at least seem to do something basically. And that impression is confirmed by the next slide, where we plot the intensity with or without the reproduction rate basically taking into account. I should be careful here because the dashed red line is not refitted in a model without RT, but it is taken from the model with RT, but then shutting off basically the RT. So then you see the contribution within that model as the difference between the black line and the dashed red line. Okay, so to conclude then on the next slide, yes, this is more like a summary. I don't think I have to repeat every bit of it, except that emphasizing that this linearity that we're exploiting is helpful in getting an easy to implement procedure. In simulations of well-specified model, it seemed to work reasonably well. However, this distinction between P and Q, that is to say the true dynamics and the risk-neutral dynamics, is something that we are not really able to identify very clearly based on only these option prices. And what I've written down in small print here is that probably if you want to make this more information on the risk premia, what you probably want to do is to combine these options data with high frequency data on the underlying, which might give you, let's say, spot volatility or so. And then you can sort of say a little bit more about the difference between P and Q, or the risk premium on volatility, basically, that you might want to allow for, at least if you want to use this for asset pricing, right? I mean, right now we're just fitting the model basically and trying to get an impression of these risk neutral parameters. Okay, that is it for me. Thank you very much for your attention and for your patience with my technical problems. Thank you.
Thank you very much. I think that despite the initial technical problems, it was an excellent talk that compensated for this. So thank you very much.
Thank you.
I'm going to stop the recording and then we can proceed to questions.